to start today with a little experiment.
Okay.
It's low stakes, I promise, wherever you are right now, unless you're driving, in which case, please keep your eyes on the road.
Yeah, definitely do that.
But if you're safe, I want you to pick an object nearby. Just, maybe it's a coffee mug, a plant, a lamp. Just look at it.
It feels pretty simple, right?
Yeah.
You just open your eyes and the world is immediately there.
It feels instant. But here's the thing that kind of keeps me up at night. In the roughly 150 milliseconds it took for you to register, hey, that's a coffee mug.
Mm-hmm.
Your brain just pulled off what is arguably the most complex biological miracle known to science.
It really is. Light hit your retina, photons got converted into electrical signals, and your visual cortex ran this massive, multi-layered computation to identify shape, texture, depth, and the concept itself.
You didn't even have to try.
Not at all.
I didn't even break a sweat. But for decades, computer scientists looked at that exact 150 millisecond miracle and just, tore their hair out.
Oh, absolutely.
They could not get a machine to do it. You could show a computer a high-definition photo of a cat, and the computer had absolutely no idea what it was looking at.
Right, because to a computer, that photo isn't a cat. It's just a spreadsheet.
A spreadsheet.
Basically. It's a massive grid of numbers representing pixel values. The computer just sees, 255, 0, 14, 88. It doesn't see whiskers or ears. It just sees data.
So today, we're doing a deep dive into how we fix that. We're looking at a bunch of foundational research papers, historical accounts of AI development, and the core mechanics of how modern computer vision actually works. Our mission here is to understand convolutional neural networks, or CNNs.
Now, I know the phrase convolutional neural network sounds like something you'd want to avoid at a party. It sounds incredibly dense.
It sounds like I need a calculator just to be having this conversation.
But the fascinating thing is, this isn't really a story about math. I mean, the math is there, obviously, but at its core, this is a story about biology. It's the story of how we taught machines to see by aggressively copying the architecture of the human eye and the brain.
And what I love about the sources we went through for this deep dive is that the real breakthrough, the aha moment, it didn't happen in some sterile server room at Google.
No, it didn't.
It started way back in the late 50s and early 60s with two guys, a Nobel Prize, and some very uncooperative cats.
Right, David Hubel and Torsten Biesel. This is essentially the creation myth of computer vision.
So set the scene for us. We're in the heyday of experimental neuroscience. What exactly were Hubel and Wiesel trying to figure out?
They were trying to map the visual cortex. They wanted to know exactly how the brain processes what the eye actually sees. So they set up an experiment where they placed these tiny microelectrodes into the visual cortex of a cat. Then they projected images onto a screen right in front of the cat. They used dots, patterns, photos, and they listened to the neurons to see when they would fire.
And initially, what happened?
Total silence. Yeah, they showed the cat all these complex things, and the neurons just wouldn't react. It was incredibly frustrating for them. I mean, they were poking around in the brain, showing it the world, and getting absolutely nothing back.
I can just imagine the panic. Like, we got this cat, we have the grant money, and we have zero data.
But then they got incredibly lucky.
How so?
As they were sliding a new glass plate into the projector, the edge of the glass cast a faint, very sharp shadow across the screen. And suddenly, crack, 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 the neurons went wild.
Wait, so it wasn't the image on the slide, it was just the edge of the physical slide.
Exactly. They realized that specific neurons in the early part of the visual cortex, they don't care about cats or faces. They care about edges, lines. One neuron fires only for a vertical line. Another fires only for a horizontal line.
So the brain is literally deconstructing the world. It's not seeing a mug, it's seeing like vertical line, curve.
But that's the very foundation. They called these simple cells. But as they looked deeper into the brain, they found what they called complex cells.
And what do those do?
These neurons took the information from the simple cells and combined them. So they responded to movement, or corners. And deeper still, neurons responded to full shapes.
So it's a hierarchy.
Hierarchy is the key word here. Vision is hierarchical. You build a face out of shapes, shapes out of lines, and lines out of pixels.
Right.
And this biological blueprint, this exact structure, is exactly what a convolutional neural network is. It's just a mathematical model of that cat's brain.
Okay, so let's bridge this gap. We have the biological theory, but how do you actually translate hierarchy into code? Because the term convolution is still hanging over our heads, and it sounds really intimidating.
It's actually beautifully simple once you visualize it.
Yeah.
Imagine you have a photograph. Now imagine you have a tiny magnifying glass.
Okay, I've got my magnifying glass.
Let's say it's a little square 3 by 3 grid. In computer vision, we call this a filter or a kernel.
A filter, got it.
You place this filter on the very top left corner of the photo. You look at those 9 pixels inside the glass. You do a little math, basically multiplying the pixels by the numbers in your filter, and you get a single score.
Okay.
Then you slide the filter 1 pixel to the right. Do it again. Slide it again.
So I'm just scanning the image, kind of like reading a book, row by row.
Exactly like that. You are creating a map of where that filter found something, and here's the absolute magic of it. Depending on the numbers inside that filter, it can do different things.
Like what?
Well, one filter might be a vertical edge detector. It will give you a really high score every single time it slides over a vertical line in the image.
Okay, but this is where I get a little stuck.
Yeah.
In the old days, didn't programmers have to manually write those filters?
Yeah.
Like, didn't someone have to sit there and code, if pixel A is black and pixel B is white, that's an edge?
Yes, and it was an absolute nightmare.
I bet.
It was so brittle. If the lighting changed even slightly, your code broke.
Hmm.
But in a modern CNN, we do not design the filters.
We don't.
No. The network learns them completely on its own.
How? I mean, how does it know what a vertical edge is if we never actually tell it?
This brings us to the engine of the whole thing. It's called backpropagation.
Backpropagation.
Right. Think of it like a teacher and a student.
Mm-hmm.
You show the completely untrained network a picture of a cat. The network just has random filters at first, so it makes a random guess. It says, I think that's a toaster.
Swing and a miss.
Exactly. So you, the teacher, say, wrong. It's a cat. Now, we have a mathematical way to measure exactly how wrong it was. We call this the loss function.
The loss function. So it's basically a grade.
Yes, a grade. And the network just got an F.
Harsh but fair.
Now, here's the backpropagation part. The network takes that F and mathematically sends the blame backward through its own layers.
Oh, wow.
It says, okay, layer 5, you messed up. Why? Because layer 4 gave you bad info. Layer 4, why were you wrong? Because layer 3 was off. And it subtly adjusts the numbers in those little magnifying glasses just a tiny bit to reduce the error for next time.
So it's just trial and error, but happening at massive speed.
Millions of times. Eventually, the network figures out, hey, every time I detect vertical edges and pointy ear shapes, the teacher gives me an A.
That's incredible.
So it essentially becomes an edge detector and an ear detector. We didn't program the biology. The math evolved it because it was simply the most efficient way to solve the puzzle we gave it.
That is wild. It just derives the rules of vision by looking at data.
Yeah.
But there is another step in this mechanics section of our sources that feels, frankly, a bit counterintuitive to me, and that's pooling.
Right, pooling.
The sources describe pooling as controlled forgetting.
Hmm.
Basically, after we scan the image with our filters, the very next step is to shrink the image, to literally throw away resolution.
Yeah.
Why on earth would we do that? We work so hard to get high-res images on our phones. Why make them blurry on purpose?
It does sound like we're shooting ourselves in the foot. But think about it this way. If I show you a picture of a cat, do you really need to know the exact pixel coordinate of its left ear to know it's a cat? Do you need to know it's at, say, pixel 402, row 500?
Not at all. I just need to know the ear is generally in the top left somewhere.
Precisely. This is a concept called translation equivariance.
Translation equivariance.
Yes. If the network memorized the exact pixel location, then if you moved the cat slightly to the right in the next photo, the network would say, I have no idea what this is. The ear moved. I'm lost.
Ah, so it would be way too rigid.
Exactly. So pooling usually involves taking a little window of pixels and just keeping the maximum value, the strongest signal from that area. It throws away the precise location but keeps the what?
It keeps the feature itself.
Right. It makes the network flexible. It learns cat, not cat at coordinate XY.
So we have convolution finding the features and pooling making it flexible. And when we stack these up, layer after layer, what actually happens? The sources mention these visualization studies where researchers can peek inside the layers.
This is where it gets genuinely spooky. When you look at layer 1 of a fully trained CNN, it looks like static, just lines and edges. It looks exactly like what Hubel and Wiesel found in the cat's brain.
The universal building blocks of sight.
Yes. Then layer 2 puts them together into corners, circles, textures. Layer 3 starts showing you honeycombs, text fragments, maybe part of wheel. And by layer 4 and 5,
What's in those?
you're seeing dog faces, you're seeing car doors, whole objects.
It's literally building the world from scratch.
It confirms that the biological hierarchy isn't just a quirky animal thing, it's the fundamental mathematical logic of vision itself.
So we have the theory, we have the architecture, but history is rarely a straight line, right? The sources outline this massive arms race of AI models, and it wasn't always success after success.
No, far from it. In fact, after the initial excitement in the 80s and 90s, the whole field hit what people call an AI winter.
What caused the freeze? Was the math wrong?
The ideas were actually there, but the computers weren't. Back in 1998, Jan LeCun built a model called Lynette. Yeah, it could read handwriting on checks. It was brilliant, but it was tiny. When people tried to build bigger ones for like real full-color photos, the computers just choked. It took entirely too long to train.
So we were just sitting around waiting for the hardware to catch up.
And it eventually did, but from a really unexpected place. Video games.
The GPU.
Right. It turns out the math required to render a highly realistic explosion in a game like Call of Duty, which is multiplying massive grids of pixels simultaneously, is the exact same math you need to run a convolutional neural network.
So gamers inadvertently saved AI research.
They absolutely did, and that leads directly to the watershed moment in 2012, a model called AlexNet.
Okay, tell me about AlexNet.
This was at a competition called ImageNet. Millions of images, thousands of categories to sort them into. AlexNet showed up, powered entirely by these gaming GPUs, and it didn't just win, it utterly destroyed the competition.
This was the moment the world woke up to deep learning.
It was the big bang of the modern AI era. AlexNet proved that if you just make the network bigger and deeper, it gets smarter. And that started the race. Everyone just started stacking more layers.
Go deep or go home.
Exactly. In 2014, you had VGGNet. They just kept stacking layers. 16 layers, 19 layers, but then they hit a wall.
What kind of wall? Hardware again?
No, a mathematical wall called the vanishing gradient.
The vanishing gradient.
Yeah. Remember we talked about backpropagation? The teacher sending the blame backward through the network?
The grading system, right? The F gets passed back.
Well, imagine a game of telephone. You whisper a message to the person next to you, and they pass it down the line. If the line is 5 people long, the message survives pretty well. If the line is 50 people long...
By the time it gets to the start of the line, the message is completely gone or garbled.
Exactly. In a very deep network, the error signal, the grade, got so incredibly weak as it traveled back that the early layers simply stopped learning. They got no feedback.
Oh.
The network stopped improving entirely. In fact, adding more layers actually made it worse.
That seems like a total paradox. A bigger brain should technically be smarter. So how did they fix the telephone line problem?
Enter ResNet in 2015. This is probably the most clever architectural tweak in this entire story. The researchers, Kaming-He and his team, added something called skip connections.
Skip connections.
Yeah.
Like a shortcut.
Exactly like a shortcut. Imagine you're hiking up a really steep mountain with a bunch of switchbacks. ResNet basically built bridges that let the hikers, which is the data, skip a layer and go straight up to the next one.
Okay.
It allowed the signal to flow freely through the network without getting diluted.
So the message doesn't have to go through every single person on the telephone line. It can just jump over them.
Yes. And the result was explosive. They didn't just go to 20 layers, they went to 152 layers.
From 20 to 152, that is a massive jump.
It was incredibly audacious, and it completely worked. 2015 was the year ResNet achieved an error rate of 3.6% on the ImageNet challenge.
For context, how does that compare to a human? Like if I sat down and tried to classify all these images manually.
A human gets about 5% wrong. Because, some of these dog breeds are genuinely really similar. It's hard to tell.
So 2015 was the year the machine officially beat the human eye.
At specific classification tasks, yes. It was a historic threshold.
But here is the catch, right? Training a 152-layer monster like ResNet takes a supercomputer. It takes massive amounts of energy and money.
True.
If I'm a startup or just a university researcher with a laptop, I can't do that. Does that mean AI vision is only for the tech giants?
For a while, it really felt that way. But then came the concept of transfer learning. And this is crucial for anyone listening who wants to actually use this technology in the real world.
The sources use a really great analogy here. The professional photographer.
It fits perfectly. Let's say you want to build an AI that detects a really rare skin disease from photos. You could try to train a network from scratch, but that's like grabbing a random person off the street and trying to teach them dermatology and how to use a camera at the exact same time.
Right, and you need millions of photos of this rare skin disease, which you probably just don't have.
Exactly. Or you could take a model like ResNet that has already been trained on millions of images from ImageNet. It's essentially already a professional photographer.
Okay.
It already knows what edges are. It fully understands lighting, curves, and complex textures.
It has the basic vision skills details locked down.
Exactly. So you take that massive pre-trained brain and you just retrain the very last layer. You tell it, okay, use all that deep knowledge about edges and shapes, but instead of looking for cats and cars, look for this specific rash.
So I don't need millions of images anymore.
No, maybe just a few hundred. This totally democratized AI. It meant you didn't need Google's data center to build something genuinely useful. You're standing on the shoulders of giants.
There's one other trick mentioned in the deep dive sources that I think is really clever. Data augmentation. It solves that same problem of having a small data set. The source calls it the martial arts approach.
Right. If you want to train a fighter, you don't just have them spar in a perfect air-conditioned gym.
Yeah.
You make them train in the rain. You put them on uneven ground. You blindfold them.
You make the training significantly harder than the actual fight.
So in AI, we do this to the images. We take a perfectly good picture of a cat and we flip it horizontally. We rotate it 15 degrees, we make it super blurry, we add static noise.
And we tell the AI, hey, this is still a cat.
Yes, it forces the AI to stop memorizing specific pixels and start actually learning concepts. It makes the model incredibly robust, because if it can recognize a blurry upside-down cat in the snow, a normal cat is going to be easy.
So for about a decade, CNNs were the undisputed kings of vision. If you were doing computer vision, you were using a CNN. But our sources mention a plot twist in the last few years. A challenger has officially entered the arena.
The Vision Transformer, or VIT.
Now, transformer is a word most people associate with ChatGPT and language models.
Correct. Transformers were originally built to process human language. But around 2020, 2021, researchers thought, wait, why can't we use this exact same architecture for images?
But language and images are totally different things. Language is a sequence of words in an order. An image is a 2D grid.
That was the big hurdle, so they came up with a very clever hack. They chop the image up into little squares. They call them patches.
Patches, okay.
And they feed those patches into the transformer sequentially, just like a sentence of words.
Okay, but why switch it all? What does a transformer do that a CNN can't do just as well?
It all comes down to how they pay attention to the data. A CNN is completely obsessed with the local area, that sliding window we talked about. It only looks at a 3 by 3 pixel grid at any given time. It builds the big picture very slowly, layer by layer.
Right, it's a bit nearsighted.
In a way, yeah. But a transformer allows every single patch of the image to talk to every other patch simultaneously, right from the first layer. It can see the global context immediately.
Oh, I get it. It looks at the whole forest at once, rather than counting individual trees.
Exactly. Especially when you have absolutely massive amounts of data, transformers start to pull ahead.
So, are CNNs dead? Is the sliding window totally obsolete now?
Not at all. It turns out CNNs are still way more efficient for many standard applications, and they are inherently better at picking up those fine local details. The absolute state-of-the-art right now is often a hybrid.
Mixing them together.
Yeah, using CNNs to catch the local details and transformers to understand the broader global context.
It's synthesis.
Exactly. But even if CNNs are sharing the spotlight now, their legacy is completely undeniable. They taught us the rules of the game. They proved that hierarchical learning building complex ideas from simple, basic blocks is the way to replicate intelligence.
Which brings us right back to where we started today. That coffee mug on your desk.
The coffee mug.
We started by saying that seeing is a miracle. And we've spent this deep dive talking about how we literally reverse engineered that miracle. We poked around in cat brains, we invented sliding window math, we built 152-layer skyscrapers of code.
And we actually succeeded. I mean, we now have machines that can diagnose cancer from a scan faster than human doctors and cars that can navigate city streets by themselves.
But there was a final thought in the notes here that really struck me. It's about the black box problem. We often talk about how we don't fully understand how these deep networks make their final decisions.
That's entirely true. When you look at those millions of weights inside a trained neural network, it's just a massive soup of numbers. We can't always trace the specific logic of how it arrived at an answer.
Which is funny because that sounds awfully familiar.
It sounds exactly like us. We don't really know how we perceive the world either. We built these incredible networks to see the world, but in the process, the most important thing we saw was a reflection of ourselves.
We built a mirror.
We really did. The machine sees like us because we built it to be us. And the fact that the pure mathematics converged so perfectly with the biological reality suggests that Maybe there is a universal rulebook for intelligence, and we are just now starting to read the first few pages.
That is definitely something to chew on. So next time you look around the room, take a second to just appreciate the sheer neural computation happening in your own head right now. It is the original technology, and frankly, it's still the best one we've got.
I couldn't agree more.
Thanks for listening to this deep dive. We'll see you next time.